guys, welcome to this second video where we're having a look at another example of loci in the complex plane. Okay, in this particular question here, okay, it's a little different from the ones that you see in your workbook. Most of the ones in your workbook don't talk about loci where the argument of some complex number is equal to something and then you're asked to describe the locus of points. Well, okay, so let's have a look at an example of this, because this is actually similar to a question that was found in an old NCA paper, so we need to have a look at this kind of question as well. Well, a couple of things to bear in mind first of all. First of all, what is the argument talking about? And this value pi over 4 is actually extremely useful when we're trying to answer this question. Now, I'll just quickly draw myself an argand diagram over here. Okay, just part of it anyway. And here's our real and imaginary axes. Now the argument of pi over 4, okay, is going to look something like this. Let's say there was a point here, and let's try and draw a line back to there. Okay, solid. Now if this angle here, the argument, remember, is the angle from the positive real axis, and if it's a positive angle, it's going anti-clockwise. Now that's actually quite useful, pi over 4, because what you've got is actually an isosceles triangle, a right-angled isosceles triangle, meaning that this distance along here, let's call that distance just x for the moment, and this distance in the imaginary distance, okay, so this real part maybe, okay, this part here is equal to this distance here. So this distance equal to this one. Now that's going to become really important when we work through this question. So how would you start this question? Well, usually if I'm not sure what to do, the first thing I'm going to do is usually to replace z with x plus iy. So let's try and see if we can simplify this argument. So we're going to have, I'm going to put the real parts together straight away. X minus 2 plus iy over x plus 5 plus iy. Now how can I do anything with that? I really can't do a lot with it. The only thing I can think of doing is to rationalize this. Okay, so let's see if rationalizing this leads to anything more useful. Now I'll just put brackets around the real part there, because we're going to end up multiplying some things together soon. Okay, so to rationalize this, we're going to use the conjugate of the denominator. Okay, and let's multiply this out, still the argument. So we're going to end up with excuse me, x minus 2 times x plus 5 minus x minus 2y plus x plus 5 times yi, and iy times iy would be I squared y squared, but I squared is equal to negative 1, so that turns out to be equal to positive y squared. And then on the bottom line, we can have x plus 5 squared, and the x plus 5 times negative iy and the iy times x plus 5, that being positive, will cancel, and then the iy times negative iy will become y squared again. Okay, so what's this turning out to be? Well, let's simplify what we can. So we're going to get x squared 5x minus 2x become plus 3x minus 10 minus, now this will be yi times x, but it's negative, so minus xyi, and negative 2 times yi, but the negative, that will become plus 2yi, and this, a little bit more simple with the signs we've got, becomes plus xyi and plus 5yi plus y squared, and all over our denominator. Okay, I'm just going to move over to here where I've got a bit more room. Okay, so we do get a couple of, well, yeah, one thing cancelling. We end up with that cancelling, but we can group together a few things. Okay, we're going to have x squared, so still the argument, okay, x squared, the 3x, is nothing else on the top line to combine with that, so still 3x minus 10, and we're going to end up with 7yi plus y squared, and our denominator is still the same. Now that's about as far as we can go. The only thing I will do to make this next step more explicit, I'm going to put all the real parts together. So they're the real parts, and this is the only imaginary bit, the 7yi, and this is over this. Now if we think about our argument being equal to pi over 4, so if the argument is equal to pi over 4, this must mean that the real part, and yes, it's over that denominator, is equal to the imaginary bit over that denominator. But let me just see if I can put that somewhere over here. If we've got something over a denominator and it's equal to something else over the same denominator, then it's really looking at, well, A would equal B then. We don't need to really worry about that denominator there. It's really, if they're over the same thing, it means that A must equal B. So if our argument is pi over 4, it means that that distance, that real distance, is equal to that imaginary distance. So from this we can therefore say that that real part there, and I am aware it's over that denominator, but as I've just mentioned over here before, the real and imaginary part are both over the same denominator. So it must mean that the top lines, okay, would equal one another. So you can put this over this denominator if we really want to. So there, but it must mean that that top line is equal to the top line here. The bottom lines are equal to one another anyway. So I'm going to remove them because it's not relevant here. So we end up with that statement there. Well, if you think about what that means, and if you've revised the work on circles, you'd say, well, hold on, this is just a circle equation. Okay, especially if I bring the 7y over here, I'm going to end up with this equation. And if I put the x squared plus 3x plus y squared minus 7y minus 10 is equal to 0, that is the equation of a circle. Now, it doesn't ask us to draw the circle. Okay, it simply says find the equation representing the locus of points. So here is our answer. We've got the locus of points, and if you wanted to, you could complete the square on the x and y terms, move the constants to the other side, end up with the standard equation of a circle. Okay, so there's another example of applying the ideas of locus and also ideas of argument. And yeah, this quite important idea that you really need to look at, okay, if they're talking about the argument, do they give us a value here which is going to allow us to equate the real and imaginary parts at some stage, which is what happened really at this point here. Alright, so I'm going to be putting a question in here, so good luck with that, and once again submit your answers and we'll see how you get on. Okay, so good luck.